Hello everyone! In this video we'll take a look at the Lewis structures of atoms, and specifically we will define valence electrons as they are critical components of every Lewis dot structure. Now as a review, we'll take a look at the structure of the atom. We know that the atom is comprised of protons and neutrons, and those are localized at the center in the atomic nucleus. We also know that protons and neutrons are 1,000 times more massive than the electrons. Therefore, we approximate that the atomic nucleus and the protons and neutrons within it do not move relative to the electrons. And conversely, the electrons then orbit around the atomic nucleus. So all of the motion within the atom is due to the electrons moving around the atomic nucleus, again, because of the mass difference. Now, you can think of this like a solar system in the sense that there's a star at the center of the solar system that is a very massive object that does not move relative to the planets that orbit around that star. This is very similar to the massive atomic nucleus in which the electrons move around that atomic nucleus. Again, just like the planets move around the star in the solar system. Now, one important thing to point out is we say that the electrons exist in the electron cloud, which suggests that the electron cloud is just some free amount of space that the electrons can freely move in any direction around that. That's not entirely true because we know from physics and quantum mechanics that there are energy levels that the electrons have to exist in. And there's a specific number of electrons that can exist in each of those energy levels. Once the first energy level gets full, then the next electron must exist in the second energy level, and so on and so forth. You can't have more than the maximum occupancy of electrons in any energy level. So if you want to continue the analogy of the solar system, you can think of the energy levels as specific orbits around the sun, just like any planet in a solar system has a very specific orbit around the sun. The planets don't exist between the orbits. They have a very defined shape in that orbit, and that's very similar to the energy levels. The number of electrons that can exist in each energy level is defined by this table. The first thing to point out is this lowercase n. That is the term that we use to define the energy level. It is called the principal quantum number, but in this context, all you need to know is that this is referring to the energy level. So if someone tells you that n equals 4 for a specific electron, you know that that electron is in the 4th energy level. That's all you really need to take home from the principal quantum number here. The next thing to look at is that in the first energy level, we have 2 electrons in that level. N equals 2, we can have 8 electrons in that level. N equals 3, we can have 18. N equals 4, we can have 32. Notice the difference between the first and second energy levels is 6 electrons. The second and third is 10 electrons. The third and fourth is 14 electrons. And as you might expect, the difference between the fourth and fifth is 18 electrons. That trend will continue on to any number of energy levels. But in this instance, we're mostly going to focus, especially in beginning of chemistry, you only focus on the first 3 and sometimes the 4th energy level, but there are elements that go beyond that. So just keep that in mind. Now, our depiction of the atom that I showed earlier works if you have only 2 electrons, because 2 or less electrons, because both of those electrons will go into the first energy level. What I'm referring to is this figure here. So these 2 electrons, without showing it, are in one energy level. Since there's only 2 electrons, they both go into the first energy level, and there's no problem, that energy level is full. However, let's say you wanted to look at something like lithium that has 3 electrons. Well, those 3 electrons cannot exist in the first energy level. So once you get to the third electron, it will go to the second energy level. And like I mentioned earlier, it's just the energy levels are just a defined orbit around the atomic nucleus that is a certain distance from the atomic nucleus. So here we have the third electron that exists out here in the second energy level, and then the 2 that can exist in the first energy level. Now you may ask, why are they in the specific position that they are? It doesn't matter where they're drawn. This just illustrates the point that there's only 2 maximum electrons in the first energy level, And then there can be up to 8 in the second. Since this is specifically lithium, we're only interested in that one electron that's there. The next thing to talk about is valence electrons. Valence electrons are defined as the electrons in the outermost energy level, or sometimes it's called the outermost shell. These electrons will be in the highest N, so again, the furthest electrons away from the atomic nucleus. These electrons are important because in all Lewis dot structures, the valence electrons are what's depicted in the Lewis dot structure. So knowing that, let's go back to the depiction of our lithium atom, this one here, and now let's use our new definition to look at how many valence electrons we have in this depiction. Well, we have the outermost shell here is n equals 2, and there's 1 electron in it. So that means that there's 1 valence electron. Okay, so now we can use this information to draw the Lewis dot structure for lithium. So the first thing you do with any Lewis dot structure is find the atom that you're interested in on the periodic table. So in this case, it's lithium. So the atomic symbol for lithium is capital L lowercase I. So this is the starting point for our Lewis dot structure, is just drawing the atomic symbol, which in this case is just Li. And then you need to draw in dots the amount of electrons, valence electrons, around the atomic symbol. So we just determined that there's 1 valence electron, so our Lewis dot structure looks like this. So the next thing to point out is commonly in periodic tables, you'll see group 13 referred to as 3A, 14 as 4A, and so on. And the reason that they do that is because group 13, or 3A, has 3 valence electrons. So the 3A just reminds you that, hey, there's 3 valence electrons in group 13. Same for 14, there's 4 valence electrons, hence the 4A. 15, there's 5 valence electrons, hence the 5A, and 16, there's 6, and 17, there's 7. Also in groups 1 and 2, there's always going to be 1 and 2 valence electrons. So this just makes it very easy to do these types of problems more quickly, because once you get to the periodic table, you can quickly find the atomic symbol for the element that you're interested in and know the number of valence electrons that that element has, and then allowing you to draw the Lewis structure just that much easier. Now let's go through a few specific examples, expanding on the lithium structure. So first one here, we have oxygen. So we know that oxygen's Lewis structure, or we know that the oxygen's atomic symbol is O, capital O, from the periodic table. We also know that it's in group 16, or 6A, so we know that it has 6 valence electrons. So then we just need to draw our atomic symbol of oxygen, which is O, and then 6 electrons around it. So notice that I'm drawing 4 electrons first, all unpaired, not pairing with each other. The reason for that is, remember from Coulombic interactions that electrons, or like charges, repel each other. Electrons all have negative charges, so they're going to disperse from one another around the atom before they are close to one another and pair up. So because of that, the first 4 were drawn like this, and now the 5th one's going to have to pair with one of them, so it can go in any orientation that you want. And I'll pair it with the top one, that's fine, but you can also pair it with the right, or any other orientation will be fine. But here is the Lewis structure of oxygen. Next, let's look at silicon. So we'll go back to our periodic table. We'll find that silicon is in group 14, or 4A. We know that its atomic symbol is capital S lowercase I. So, and because it's in group 14, we know that it has 4 valence electrons. So we start with our capital S lowercase I, and then we draw our 4 valence electrons around the atomic symbol. And in this case, we don't have to worry about pairing any of the electrons because we only had 4. So we were able to disperse them from one another to get the like charges away from each other. So here we have the final Lewis structure of silicon. And then lastly, we'll look at chlorine. So we go back to the periodic table. We see that chlorine is in group 17, or 7A. So we know that it has 7 valence electrons. We also know that its atomic symbol is capital C lowercase l. So we draw our chlorine, capital C lowercase l, and then we draw 7 valence electrons around the atomic symbol. So again, we start with our 4 unpaired, and then now we're going to have to pair 3 of them because we still have 3 valence electrons left to get to the 7 total. So a valence structure, or a Lewis dot structure for chlorine would look like this. Again, you can put the pairs in any orientation that you want, like the single chlorine could be, the single electron rather, could be on the right if you wanted. So like this could be an acceptable structure, or any of the other possible orientations. It doesn't matter, as long as you have 7 total valence electrons and 3 sets are paired. It is important to mention here that the comparison between the atomic structure and the structure of a solar system is somewhat incomplete, but we're going to use it as an introduction to the atomic structure because it explains many chemical properties that we see in chemical reactions and atoms themselves. So, and then we can use this incomplete structure and build on it to create what is now accepted as the modern depiction of the atom. So I just want to mention that it isn't complete, but you can certainly use it to begin to understand this, and we'll build on the atomic structure into the more complete picture in later videos. All right, and that'll do it for this video. So if you learned something, please leave a like and subscribe to the channel if you haven't already. And thank you for watching. I'll see you in the next video.